Modern classical encryption systems cannot guarantee complete data security, for they rely on the fact that an eavesdropper does not have enough computing power. The arrival of quantum computers will make currently used systems vulnerable and thus threaten national and commercial secrets, as well as the entire global infrastructure in general. The increase in the length of encryption keys loads the infrastructure, though giving a short respite only. Back in 2009, the 768-bit RSA key was hacked. The 1024-bit RSA key was recognized as unreliable back in 2010. A fundamentally different approach to data protection is needed. Therefore, an alternative approach is being developed, that is quantum cryptography, which no longer depends on eavesdroppers' computing powers. It means cryptographic strength remains unchanged over time, unlike for classical encryption algorithms. The cryptography of the future is quantum cryptography. Unlike classical algorithmic approaches, quantum protection is based on the fundamental laws of physics and photon properties, since its quantum state cannot be measured without destroying it. The principle of quantum key distribution is the transmission of information encoded in the parameters of a light quanta, i.e. photons, for example, to polarization states. Alice generates a photon and encodes it, choosing the polarization randomly from two pairs, bases, in each of which the photon states are clearly distinguishable and can be matched with a binary number, 0 or 1. Bob measures the polarization of the transmitted photons, trying to guess the bases used by Alice, and then informs Alice on the bases used. If Bob's guess is right, he receives a certain binary number which is the same as Alice's one. Otherwise, for an incorrect basis choice, the result is discarded. This procedure of the basis checking is called key sifting, and the binary set, which is the same for Alice and Bob, is called the raw key. The raw key is then additionally processed. During the result exchange over an open communication channel, the errors are corrected, and the possibility of an eavesdropper presence in the channel is estimated. In this case, a part of the key bits is revealed, and another one remains secret. As a result, Alice and Bob receive the same key only they know. The message is encrypted using the secret key. If Eve intervenes in the process during the key distribution, she is forced to make the same measurement of photons as Bob, and then send a new photon with the basis needed, thus trying to imitate Alice. However, the probability of a wrong basis choice will be high. Due to errors present in the transmission channel, Alice and Bob will immediately detect Eve and terminate the quantum communication session. After that, Alice will start generating a new key. Quantum cryptography does not replace, but improves existing crypto systems, allowing keys to be renewed both frequently and automatically. This makes it possible to minimize the key lifetime, enhancing the security of a crypto system. Additionally, it eliminates the need to transfer the key in a manual mode on a physical carrier. Specialists from ITMO University have developed a unique method, that is, subcarrier wave quantum key distribution. Its advantages are the following: working in standard fiber optic networks as well as in atmospheric channels, efficient creation of additional channels which increases either speed or number of users, implementation of different QKD systems of the same technology, backbone networks, urban systems, economically efficient user stations and atmospheric clients, resistance to external influences on a communication channel, high speed and distance of information transmission. Together with ITMO University, Quantelecom has combined a system for subcarrier wave quantum key distribution and a classical means of cryptographic information protection in a single construct. This makes it possible to use existing fiber optic communication networks and build various network topologies for end users with a previously unattainable level of security. By 2022, the damage from cyber attacks will be $8 trillion. The amount of data that needs protection is growing. Investment in IT infrastructure for storing and protecting information is increasing. USA, China, and Europe are investing in quantum technologies. All this is a threat of protection for carriers of critical information even today. Quantelecom offers a solution that will provide protection of confidential data and significant savings on the consequences of data leakage, as well as the infrastructure for the future that has already arrived.